In this class, I want to explain movements and the concept of operations on random variables. We have two types of movements. The first type is movements about the origin. Movements about the origin. And second is movements about mean or central movements. What is the importance of this concept movements? We came to know how the random variable is spreaded with respect to the origin, that is in the first case, and with respect to the mean of the variable. So from that you are going to get the nature of the random variable, how it gets spreaded, and where the highest amount of the random variable gets concentrated, where its value is less. These things can be obtained by finding the moments. After getting all these things, you can analyze the random variable. You can do the necessary things. Suppose take your random variable as a noise signal. If you find how the noise gets spreaded with respect to the origin or with respect to the mean, and where the noise signal is having high value, where it is low, and by using proper circuitry and by using proper analysis, you can eliminate that noise or you can reduce the effect of noise. So that is the significance of movements. Okay. So now let me start the first one. Movements about origin. Okay. So now let g of x, the function of random variable, such that g of x is equal to x power n for n is 0, 1, 2, 3, etc. Then the expected value of the function of g of x, then e of g of x is called, e of g of x is called movements about origin. Okay. Then what is e of g of x? We know it already from the concept of expectation. It is simply integral minus infinity to infinite g of x into fx of x dx. And substitute this g of x. What is this? X power n into fx of x dx. So this is your e of x power n. Okay. And that is denoted by mn. Okay. So now this is the formula to find movements about origin. This is for continuous case, and for the discrete, mn is e of x power n is sigma I is from 1 to n xi power n p of xi. Always verify the notations in discrete and continuous cases. Let me write this discrete. Whenever you have integral and continuous, you have to write sigma in discrete. And in the place of x, write xi. In the place of fx of x, you have to write p of xi. Okay, so this gives you the moments about origin. Now, if n equal to 0. Okay, so now keep n equal to 0 here. So this mn becomes m0. That is integral minus infinity to infinite. Yes, in the place of x power n, you have to take x power 0. That is fx of x dx. So what is this? X power 0 is 1 into fx of x dx. So what is this? It's nothing but 1. So simply m0 is 1. What is this integral minus infinity to infinite fx of x dx? The value is 1 and it is nothing but area under density curve. You know it already. Okay. So what is m0? m0 is 1. So what is the conclusion? Zeroth moment of x is m0, that is equal to 1, and it gives area under density curve. Okay. Then if n equal to 1, yes, now write implies m1. Yes, just keep in the place of n, keep 1. It is e of x. Integral minus infinity to infinite x into fx of x dx. Yes, these are capitals. E of is always capital. Inside that big bracket, always this is capital X. And only this in the integration or in the summation you have to write small. Okay. So now what is this? This is nothing but your e of x. It's nothing but x bar. X bar. So what is m1? m1 is x bar. Or you can say it is e of x. What is this? This is nothing but mean. Nothing but mean. So the first moment is equal to the mean value. So this is 0th moment. And this is first moment. First moment. Okay. Now take n is equal to 2. So you're going to get m2. So it is e of x square. Integral minus infinity to infinite x square fx of x dx. Okay, this is called second moment. And the name of the second moment is mean square value. So this is about moments about origin. So here you have seen the general expression for moments. It is simply mn equal to integral minus infinity to infinite x power n fx of x dx. It's nothing but expectation of the function of the random variable g of x, where g of x is defined as x power n. Okay. Then, yes, we have taken three cases: n equal to 0, n equal to 1 and n equal to 2. At n equal to 0, we got 0th moment whose value is 1. And n equal to 1, we got first moment whose value is mean. And n equal to 2, we got second moment whose value is called mean square value. Then we'll see moments about mean. Moments about mean. Okay, These are represented by mu n. Okay. And here the random variable function g of x is x minus x bar whole power n. In the previous moments about origin concept, g of x is x power n. Now it is x minus x bar whole power n for n is equal to 0, 1, 2. Okay. So what is x bar here? X bar is mean. X bar is mean. Therefore, the expectation of g of x which is nothing but x minus x bar whole power n. Simply you write integral minus infinity to infinite x minus x bar whole power n fx of x dx. Okay. This is called the moments about mean. Okay. So this is called moments about mean, that is represented by mu n. Okay. So this is for continuous case. And continuous case. For discrete, I'll directly write the formula. Sorry, sigma I is from 1 to n. Xi minus x bar whole power n into P of xi. This is for discrete case. Okay. So mu n is also called central moment. Central moments. Then take cases like in the previous concept. Take cases. If n is equal to 0, okay, then I'll get mu naught, that is equal to integral minus infinity to infinite, just in the place of n keep 0, x minus x bar whole power 0 into fx of x dx. Okay. Yes. 0 is 1 and fx of x dx. Again, this is nothing but area under the density curve. So it is equal to 1. So the answer is 1, implies your mu naught is 1. Mu naught is 1. So the 0th central moment is mu naught, that is equal to 1, and it gives the area under density curve. And if you observe the previous one, moments about origin, there also the 0th moment m naught is also 1. So implies you can write mu naught, that is equal to m naught, that is equal to 1. Very important formula. Okay. Then if n is equal to 1, implies mu 1 is equal to e of x minus x bar, because n is 1, is equal to integral minus infinity to infinite x minus x bar into fx of x dx. Okay, simply just you multiply x into fx of x dx minus integral minus infinity to infinite x bar into fx of x dx. So what is this? This is the formula of expectation of x, and that is represented by x bar minus, you know, the x bar mean. The mean value is always a numerical value. Okay, so it's a constant. So you have to make it outside. Then it will be integral minus infinity to infinite fx of x dx. Again, what is this? This is area under density curve, that is equal to 1. So it is x bar minus x bar, that is 0. Okay, so it implies mu 1 is equal to 0. Hence, the first central moment of x is always equal to 0. Okay, first central moment. First central moment, mu 1 is 0. Then, if n is equal to 2, it implies mu 2, that is e of x minus x bar whole square, integral minus infinity to infinite x minus x bar whole square into fx of x dx. Okay, this second central moment is called variance. Very important topic, variance. Okay, so variance is mu 2, that is integral minus infinity to infinite x minus x bar whole square into fx of x dx in the case of continuous, and mu 2 equal to sigma I is from 1 to n xi minus x bar whole square into p of xi in the case of discrete. What is the second central moment? The second central moment is mu 2, that is represented by sigma x square. Next is about the concept standard deviation. In connection with the variance, you have standard deviation. The standard deviation is represented by sigma x, which is nothing but root to sigma x square, means root variance. Root variance, that is root e of x minus x bar whole square. Standard deviation is d. Now if you take n is equal to 3, the next case is n is equal to 3. We are going to get mu 3, and that is given by e of x minus x bar whole cube, that is integral minus infinity to infinite x minus x bar whole cube fx of x dx. Okay, so what is this mu 3? Mu 3, the third central moment. Third central moment, mu 3 is called skew. Skew. So in the continuous case, simply you write this expression, mu 3 is a of x minus x bar whole cube integral minus infinity to infinite x minus x bar whole cube into fx of x dx. And in the discrete case, mu 3 is sigma I is from 1 to n xi minus x bar whole cube into p of xi. Okay, so it is skew. Now in connection with the third central moment, we have coefficient of skewness. The coefficient of skewness is the ratio of third central moment to the cube of standard deviation. Cube of standard deviation. What is the cube of standard deviation? Standard deviation is represented by sigma x, its cube. Okay, so it is mu 3 by standard deviation. You know it is the root of variance. Okay, so you can write it as sigma x square means the variance power 3 by 2, or in an expanded way it is mu 3 by e of x minus x bar whole square power 3 by 2. So this is your coefficient of skewness. Okay, this is the concept moments about mean or central moments. I'll write the summary moments about origin and moments about origin. The 0th moment m0 is 1. The first moment m1 is x bar is nothing but mean. The second moment m2 is nothing but mean square value. And next, moments about mean. The 0th central moment is 1 and the first central moment is 0 and the second central moment is nothing but variance and the third central moment is nothing but skew. Okay, just remember these things and their formulas.
Thank you for watching this video. If you like this video, please don't forget to like, share and subscribe.